Imagine dropping like $500,000 on a state-of-the-art vertical machining center.
Oh, yeah. That is a massive investment for any shop.
Right, so you get it all rigged, powered up, and on the very first heavy cut, you just watch in absolute horror as the spindle screams, and the entire machine basically vibrates itself to pieces.
And the crazy part is, that usually happens all because of a tiny hidden mechanical choice you didn't even realize you made.
Exactly. Welcome to today's deep dive, where we are looking at exactly that scenario. Because this hidden choice, it dictates whether your shop thrives or just bleeds money.
It really does. It happens way more often than shop owners want to admit, honestly. Pick the wrong physical guide rails for your specific production needs and, well, the consequences compound fast.
We're talking shattered carbide end mills, scrapped parts, missed tolerances.
Yeah, totally. A machine that is actively losing you money instead of printing it.
Okay, let's unpack this because this really is a critical crossroads for you, the listener, if you're running a shop floor. Our mission today is to decode this massive choice using a whole stack of manufacturer specs and engineering notes.
Which really boils down to two contenders, right? Linear guide rails versus boxway hard rails.
Right, and we aren't just talking about a minor spec sheet difference here. These are two fundamentally opposed philosophies of how a machine handles the physics of cutting metal.
At its core, yeah, this choice forces you to prioritize. You have to understand the raw physics of your specific production environment. Because there is no universal solution here.
So what are the two sides?
Well, on one side, you have linear rails. They utilize rolling friction, prioritizing blistering speed and rapid movement, which is typically for lighter metals.
On the other side?
On the other side, boxway hard rails.
Mm.
They rely on sliding friction, prioritizing extreme rigidity and shock absorption for, heavy, punishing cutting operations.
Two totally different mechanical philosophies, which means we need to look at the business outcomes of both. And the most logical starting point for us is cycle time.
Absolutely. Because time is money.
Exactly. If you want to make money, you need to make parts faster, which requires looking at how these massive machine tables physically travel along these hidden rails.
Right. And friction controls that speed. It is the fundamental physical bottleneck dictating how quickly the servo motors can actually position the workpiece under the spindle.
Let's visualize the mechanical difference here for a second. Imagine rollerblading across a perfectly smooth, polished concrete floor.
Okay, very low resistance.
Right. Now compare that to dragging a solid, heavy wooden crate across that exact same floor. That is essentially the mechanical divide we are looking at.
That's a great way to picture it.
Yeah, so linear rails are the rollerblades. The system uses these tiny steel balls, or sometimes cylindrical rollers, packed inside a modular metal block.
And those balls roll smoothly along a hardened steel track.
Right, creating an environment of extremely low rolling friction.
What's fascinating here is what that low friction actually unlocks on the factory floor. Because the physical resistance is so minimal, the machine's servo motors are barely breaking a sweat to push a heavy table around.
They're just gliding.
They glide, exactly. This low-drag environment allows a VMC equipped with linear rails to reach rapid traverse speeds of 30, 40, and in high-end machines, over 60 meters per minute.
Wait, 60 meters per minute? For a machine that weighs as much as a small tank?
Yeah.
That is almost terrifying to picture moving that fast.
It is an aggressive amount of speed, no doubt about it. But let's look at the economics of that speed. For a shop producing, say, aluminum enclosures for electronics or small aerospace brackets.
Where you're doing a lot of fast light cutting?
Right. The spindle is zipping around, drilling hundreds of holes, making quick passes. Every single second the machine spends just moving through empty air from one hole to the next.
It is dead time.
Yes, dead time.
And dead time is unbillable time. Yeah.
Precisely the issue. If you save just 2 seconds per part on rapid movements, and you are running a contract for 100,000 units over the year, well, linear rails just saved you hundreds of hours of spindle time.
Wow. You essentially gained the production capacity of a whole second machine just by eliminating that friction.
Exactly.
Okay, that makes total sense for the rollerblades. But let's look at the wooden crate. We have hard rails, which they don't use rolling elements at all, right?
No, not at all. They use flat, solid cast iron surfaces physically sliding directly against each other.
Wait, if you're dragging iron on iron, that creates massive sliding friction, and doesn't that mean you are generating massive amounts of heat?
Oh, a ton of heat.
Doesn't heat warp metal? How does a precision machine function if its own rails are expanding from the friction?
Well, that vulnerability is exactly why hard rails are strictly limited by physics. The extreme heat generated by that sliding action is the absolute enemy of precision.
Because things start expanding.
Right. If you push a hard rail system past roughly 15 meters per minute, the thermal dynamics just take over. The metal components of the machine physically expand.
Even a microscopic expansion would completely throw off the positional accuracy, right?
Absolutely.
Like, you tell a machine to go to a specific coordinate, but the rail has grown by a few tenths of a thou, so the tool cuts in the totally wrong place.
And suddenly your part is out of tolerance, the quality control team flags it, and you've just manufactured a very expensive paperweight.
Yikes.
So to prevent that thermal expansion, the machine must run slowly. It has
Yeah.
to actively keep the rapid traverse speeds under that 15 meter per minute threshold.
Okay, so if linear rails are saving hundreds of hours of cycle time by hitting 60 meters per minute, and hard rails are artificially throttled at 15 just to keep from warping,
Yeah.
why would anyone ever choose hard rails? Speed is money. Why not just slap linear rails on every single machine in the shop?
Because machining isn't just about moving gracefully through empty space to get to the next coordinate. Machining is an inherently violent process.
You are forcefully driving a hardened cutting tool into raw metal to physically rip material away.
Exactly. And when it comes to that level of violence, speed must yield to force. Think about a shop that isn't cutting light aluminum, but rather roughing out massive blocks of Inconel or like aerospace-grade titanium.
Oh, wait, I'm picturing this setup now. If you take a massive aggressive cut in titanium, that creates an incredibly violent shockwave when the tool hits the metal.
A huge shockwave, yes.
So if linear rails are essentially just riding on these tiny steel balls, wouldn't a heavy, violent shockwave from milling just obliterate those tiny points of contact?
You nailed it. That vulnerability actually has a name in engineering. It's called point contact.
Point contact, okay.
Yeah, those little steel balls inside the modular block, they only touch the rail track at a microscopic singular dot. And point contact is terribly inefficient at absorbing or transferring heavy shock forces.
Because the energy just has nowhere to go.
Right, so all that violent vibration from a heavy titanium cut gets bottlenecked at these microscopic dots of steel.
And what does that look like on the shop floor?
The results are immediate and loud. When you attempt heavy milling on linear rails, the violent shock waves pass right through those tiny balls and bounce back into the machine frame.
The whole thing shapes.
The whole setup chatters. You can actually hear the high-pitched squeal from across the shop. And all that vibration transfers directly into your expensive carbide cutting tool.
And carbide is incredibly hard, which also makes it brittle.
Very brittle.
So if it vibrates too much, it chips. You could be snapping a $200 end mill every 20 minutes.
Easily. Not to mention, under extreme continuous loads, the immense pressure actually causes the steel balls inside the linear block to physically deform or even shatter.
So you are trading structural integrity for rapid speed.
Exactly. And this is why the hard rail solution is mandatory for heavy cutting. The manufacturing architecture of a boxway hard rail is entirely different from a bolted-on linear track.
They are cast directly into the machine, aren't they?
They are. The foundry casts the hard rails directly into the main machine bed as one solid, continuous piece of incredibly thick iron.
It's literally the actual skeleton of the machine.
Yes, because the sliding surfaces are perfectly flat and machined to mate exactly with each other, you achieve full surface contact.
Which completely eliminates the point contact bottleneck.
Precisely. The force is distributed over a massive area instead of a microscopic dot.
And that large flat contact area acts as a massive energy absorber. Right.
The thick, solid cast iron literally swallows the vibrations. You can plunge a heavy roughing mill into a block of 4140 steel, generating massive violent forces, and the machine stays perfectly quiet and rigidly locked in place.
Wow. So the surface contact grounds the shockwave, protecting your tools and making sure the machine doesn't just shake itself apart.
That's exactly it.
Here's where it gets really interesting, though. Because surviving the violent dynamic shock of a heavy cut is one thing, but we also have to look at static loads.
The continuous crushing weight.
Right. The weight of massive materials. Think about the scale of mold making. We're talking about car body molds or massive plastic injection molds for appliance parts. Those weigh thousands of kilograms.
Oh, absolutely.
It's literally a multi-ton block of solid steel just sitting on the machine table for days at a time. It is honestly incredible to me that the VMC table doesn't just bend under the immense pressure of a large spindle pushing a tool deep into a block of steel that heavy.
Well, if we connect this to the bigger picture of factory longevity and sustained precision, This static load capacity becomes the defining factor for shop owners.
Because for massive molds, you need extreme rigidity that won't degrade over like a 10-year lifespan.
Right. And because hard rail VMCs use those thick integrated rectangular castings, they can handle the continuous pushing force of a large spindle driving into hard steel without flinching.
The massive iron rails simply do not bend under the pressure.
Meaning the machine maintains a perfectly straight cutting path, even when a 5-ton block of steel is sitting on it, and the spindle is pushing laterally with thousands of pounds of force.
Which is wild to think about.
It is, but maintaining that straight path is non-negotiable. If the rail deflects even a fraction of a millimeter under that weight, the final dimensions of your mold are compromised.
Ruined, basically.
Yeah. Furthermore, these hard rails go through intensive thermal treatments. During manufacturing, the iron rails are quenched and ground.
Making the surface extremely hard and remarkably wear-resistant.
Exactly. A high-quality hard rail machine handles those thousands of kilograms year after year without losing its geometric precision.
Okay, let's play out the alternative here. What happens if a shop tries to run a 5-ton injection mold on a machine equipped with linear rails?
The modular blocks fail, and it is a very expensive failure.
Because of the weight.
The continuous crushing weight of the mold combined with the extreme lateral pushing forces of deep cuts places an unbearable load on those tiny rolling elements.
So over time, the linear blocks physically deform.
Right. The rolling balls wear out, they flatten, or they just break under that sustained load.
And replacing worn linear blocks isn't just buying a new part, it's tearing down the machine, losing days of production, and having to trim and recalibrate the entire geometry of the table.
It's a massive hidden cost. Linear rails just don't have the long-term structural support for heavy mold making.
That structural reality totally dictates the tooling strategy.
Mm-hmm.
But surviving the heavy weight and the violent shock waves is really only half the battle.
Oh, for sure. Keeping the machine intact doesn't matter if the customer rejects the final product.
Exactly. Which brings us to the surface finish of the metal itself, because a customer buying a multi-ton mold for car parts is going to inspect that final surface under a microscope.
Oh, they scrutinize every millimeter.
Right. So how does the choice of a hidden guide rail physically alter the actual finish of the part coming out of the machine?
To understand the surface finish, we really have to look at the physics of machining high-hardness materials.
Okay.
When a cutting tool engages with pre-hardened tool steel, the steel doesn't just passively yield to the cutter, it actively fights back.
It's like pushing against it.
Right. This creates a mechanical phenomenon called pushback force. The hard steel is physically trying to repel the cutting tool away from its surface.
It is almost like trying to carve a solid block of ice with a dull knife.
That's a great analogy.
The ice is so hard and the resistance is so high that the blade just wants to skip and bounce off the surface instead of slicing smoothly through it.
And that skipping and bouncing is the exact physical manifestation of pushback force, happening on a microscopic level. The hard metal repels the tool, creating rapid, high-frequency vibrations.
Wow.
And this is the precise moment where the design of linear rails truly suffers. Under those strong pushback forces, the tiny rolling balls inside the linear block compress.
Because they are just little hollow-feeling spheres taking the full brunt of a massive repulsive force.
Exactly. We call this microdeformation. As the tiny internal parts compress under the load, the entire linear block shifts up and down microscopically.
So the machine table is literally bouncing.
Yes. So as the cutting tool moves across the hard steel part, it is rapidly bouncing against the metal instead of gliding through it.
And that bouncing translates directly into the metal. Instead of a smooth, polished mold cavity, you get ugly, prominent chatter marks and wave patterns all across the surface.
Highly visible chatter marks that completely ruin the aerodynamics or aesthetics of the final molded part.
That's a disaster for a mold maker.
It really is.
Yeah.
I should note, though, that some machine manufacturers try to compensate for this vulnerability by upgrading to roller-type linear rails.
Okay, what's that?
Well, instead of round steel balls, they pack the modular blocks with thicker cylindrical rollers.
Interesting. Does that solve the microdeformation problem? I mean, a cylinder has more contact area than a sphere.
It increases the rigidity, certainly, but it does not eliminate the problem. The cylindrical rollers still suffer from compression under high pushback forces. They are still modular elements inside a block. They still cannot beat the monolithic rigidity of hard rails.
Because a solid cast iron hard rail simply does not compress.
Exactly. Boxway hard rails, with their massive sliding contact area, act as an uncompromising shock absorber.
Right.
When that high hardness tool, steel, pushes back against the cutter, the cast iron absorbs the force and neutralizes the high-frequency vibrations instantly. There is zero micro-deformation.
So the tool stays perfectly locked in a rigidly straight path,
It doesn't bounce at all. It just shears the metal cleanly away.
leaving behind a smooth, mirror-like finish with incredibly low surface roughness.
Yes. And in mold making, achieving that mirror finish directly on the machine saves countless hours of manual polishing. It basically guarantees the customer accepts the part.
So what does this all mean for you, the listener, who might be evaluating a massive equipment purchase right now, or just trying to understand why your shop floor operates the way it does?
It means that picking your VMC guide rail isn't a debate about which technology is inherently better or more advanced.
Right, it's not a contest. It is strictly an exercise in matching the mechanical physics to your specific scope of work. If your business model is built on high volume, light duty machining like churning out thousands of aluminum heat sinks or electronic brackets, then linear rails are absolutely your ticket.
The low rolling friction unlocks those 60-meter-per-minute rapid speeds, shaving seconds off every part and compounding into massive annual gains in cycle time.
But if your business steps into the heavy-duty arena, the calculus completely flips.
It totally flips. If you are dealing with massive multi-ton molds, heavy roughing of solid steel blocks, and punishing cuts in hard metals, you cannot rely on tiny rolling balls.
No way. You require the rigid, vibration-swallowing power of boxway hard rails. You have to build the foundation around the violence of the work it is destined to do.
Which raises an important question for anyone evaluating a machine tool. What is the actual cost of your guide rail?
Yeah, that's the real question.
Because understanding these fundamental differences, rolling versus sliding friction, point contact versus full surface contact, is the only way to accurately forecast your tooling costs, your scrap rate, and your true profit margins.
It's the hidden variable that dictates everything else. But before we wrap up this deep dive, I want to leave you with a thought to mull over on your own.
Okay, let's hear it.
We've established that the ultimate ceiling for those incredibly rigid hard rails is the heat expansion caused by sliding friction at high speeds, right?
Right.
That 15-meter-per-minute speed limit is basically dictated by thermodynamics. But technology in manufacturing rarely stands still. How might future hybrid machining centers evolve to cheat those physics?
Oh, that's a fascinating thought.
Imagine advanced extreme cooling technologies, perhaps cryogenic fluids or active thermal canceling software designed to completely neutralize that sliding friction heat in real time.
That would change everything.
Could we one day soon see a machine that possesses the massive vibration-killing shock absorption of a monolithic cast iron hard rail, but runs at the blistering 60-meter-per-minute speeds of a linear one?
That would be the ultimate disruption to the factory floor.
It really would. Until then, keep digging, keep learning, and we'll see you on the next deep dive.